qualitative versus quantitative data. If you're in the lab, you may have already heard me go on and on about this, so you've got a good head start. How is qualitative data different from quantitative data? So qualitative data focuses on qualities, descriptions, conveyed with words or sketches. So in this case, for this image, qualitative data would be the rocks are steaming. Okay, they're giving off steam. That's the quality of these rocks. I don't know how much steam, I don't know the temperature of the steam, I just know they're giving off steam, which is still extremely important to know, but it's not quantitative. Quantitative data is from numeric measurements. It's conveyed with numbers. So in this case, we might say the temperature of the rocks from the thermal instrument was 200 degrees C. Okay, we've got a number, a measurement. It's precise. 200 degrees C is the same all over the planet, whereas the rocks are giving off some steam might mean something different. Maybe somebody thinks it's a little bit of steam. Maybe somebody imagines it's erupting a column of steam. We don't know. But knowing that they're giving off steam, we know it's active, and that's very important. Knowing that it's 200 degrees C is also very important. So that's the difference between qualitative and quantitative. Qualitative is with words, its descriptions, its qualities. Quantitative is with numbers. It is quantitative. Sorry, it's from quantities. Now, referring to differences in topography. So how do we measure geologic features? How can difference in topography be conveyed? So what you want to do first is label the diagram on the left. The first thing we're going to label is elevation, which is the height above sea level. The next thing we're going to label is relief, which is elevation difference. So that answers your first question. How can difference in topography be conveyed? With relief. Okay, if you're describing the relief of an area, you're talking about the difference between the highest elevation and the lowest elevation. And then the third of the boxes for that image on the left is steepness of slope. So the best way to talk about steepness of slope is with a precise angle measurement, but you can also be more qualitative about it and say it is moderately steep or very steep, or has a very shallow slope if it's not very steep. So these are all different ways to talk about topography from one place to another. Right, now density versus weight. You've got a couple questions in that box up above that you were just writing in. How do we measure the length, area, and volume? So if you're thinking about these blocks that are in this image here, how might we measure the length there? What are some units we could use? Okay, in this case, maybe it's inches. Okay, the length of this box, maybe it's 1 inch by 1 inch. Okay, so that's a single dimension. The length is just one side. Okay, the area is going to give us two sides, so it might be 1 inch times 1 inch. The length times the width gives us the area. So area would be inches squared. And then finally, the volume is going to be the length times the width times the height. So in this case, it's a cube, so it's 1 inch length, 1 inch width, 1 inch height, all times one another, so you get 1 inch cubed. It's 1 cubic inch. Alright, so that's what we can write down where it says calculate the area and volume of the block. Why don't we label that block so it's 2 inches on each side. Okay, so length, width, and height all equal 2 for this block you're calculating on. So for area, again, area is length times width. So in this case, we've got 2 inches times 2 inches. This is on your notes, by the way. It has nothing to do with the slide right now. So 2 inches times 2 inches equals 4 inches squared. Okay, whereas the volume, we're going to have length times width times height. So 2 inches times 2 inches times 2 inches. So we'll end up with 8 inches cubed. 2 times 2 is 4, times 2 is 8 inches cubed. Alright. So that takes care of refamiliarizing yourself with length, area, and volume, I hope. So now back to our slideshow. What can you infer about the differences between the 3 blocks immersed in water? Okay, we've got one floating, one sort of hovering in the middle, and one that sinks to the bottom. Okay, so hopefully you'll notice that the least dense is the one that's floating on the left. The one in the middle probably has an equal density to the water, and the one on the right has the most density. It is more dense than the water, so it sinks down to the bottom. To figure out density, we use mass divided by volume. Okay, so in your notes where it says define density, density equals mass divided by volume. Right, that's different from weight. Weight is the downward force an object exerts under gravity. So we would calculate that by mass times gravity. Weight is how much downward force an object exerts under gravity. So this depends both on mass and on gravity. So usually when we think of mass, we just think of weight, but it has everything to do with gravity. So this example is a good one to try and understand that. Will this person have the same weight on the Earth and on the Moon? Well, if their mass is not changing, what's changing is gravity. So there is more gravity on Earth, so there's more force pulling them down than there is on the Moon. They're going to weigh less on the Moon because there's less gravity pulling them down towards the surface. So if you want a quick weight loss plan, just go live on the Moon. Alright, so let's calculate the density of our little imaginary block. If our block has a mass of 5 grams, what is its density? So our density is, again, mass divided by volume. So in this case, we've got 5 grams as our mass, and our volume is 8 inches cubed. So it would be 5 grams over 8 inches cubed. Okay, that would be our density. Okay, before we move on to our geologic time, you've got a question at the beginning of this note page. Give an example of a rate and how a rate is calculated. So the best example of a rate is one that we use every day when we're driving around town. So that is miles per hour, which is just distance per time. Distance over time. Okay, so something is changing over time. That's what a rate is. In the case of miles per hour, we're talking about distance, but we could be talking about how many students drop out each semester. Okay, that could be displayed as a rate as well. 5 students each semester. It's something changing over a period of time. That's all it is. Alright, now we can talk about geologic time. So back to our slideshow. We've got 4 main parts of geologic time, and they're all based on fossils. Okay, so this is all based on looking at the rock record and seeing in the rock something major happened here. Something big changed at this point. And so scientists decided, all right, this is a cutoff, and that's how it gets a different name. Usually the name is based on the location where the rocks representative of that change were first found. So let's take a look at these labels. We've got the Precambrian as the oldest, so we're going to fill in these main chapters here. Number 1 is the Precambrian. The amount of time is 4.5 billion with a B. 4.5 billion years ago. You can represent that with a B-A, capital B-A. Sometimes it's represented with a capital G-A. So our image here says 4,500 MA. MA just means million years ago. So 4,500 million is 4.5 billion. So whatever you prefer to write. Okay, that's the start time. The end time is 542 million years ago. That's where it switched into the next chapter, which is the Paleozoic. So number 2 is the Paleozoic, and that's from 542 million years ago, MA, to 251 million years ago. 542 million years ago to 251 million years ago. At 251, it switches into the Mesozoic. So number 3 is Mesozoic. The amount of time for that is 542 million years ago. I'm sorry, scratch that. 251 million years ago to 65 million years ago. Okay, that's the green section we're looking at here. The Mesozoic is 251 million years ago, and it ended 65 million years ago. The last one here is the Cenozoic. So number 4 is Cenozoic, and that's 65 million years ago to present, to now. So make sure you have those all written down with the time period. Then we're going to talk about the life that existed at each one. All right. So the life for the Precambrian is before shells and hard parts. So these are all single cell organisms or small invertebrates. Okay, animals did not have shells or hard parts. So these are all invertebrates. Things like jellyfish or bacteria. Nothing with exoskeleton. Or an internal skeleton for that matter. Okay, no bones and no shells. The Paleozoic. So at 542 million years ago, there was this amazing change in the rocks. We call it the Cambrian explosion. And this is where life suddenly diversifies in the rock record. We have the appearance of fish, plants, insects, and reptiles. So the Paleozoic has the appearance of fish, plants, insects, and reptiles. The Mesozoic is the dinosaurs are in charge. So we've got the dinosaurs and the first flowering plants. That is the life that is dominating the planet during that period between 251 and 65 million years ago. And then the most recent mammals are the dominant life form. Okay, so life there is mammals. Of course, there are all sorts of other things other than mammals, but mammals are the dominant life form at this time. So which chapter is longest and which one is shortest? Well, we've got the Precambrian that's got this jagged cutoff at the end from 4.5 billion to 542 million. That's definitely the longest. The Precambrian is the longest. And then the shortest is going to be the Cenozoic. So far it's just 65 million years. So that's our shortest chapter. So another way to look at this, because it's hard to think in billions and millions, so if we put it on a time scale we're familiar with, it's a lot easier to look at. So we were going to put this on 1 year calendar. So we start out at January 1. It is the Precambrian. Okay, the Precambrian takes up the first 10 months and part of November. The oldest dated rocks, about 3.9 to 4 billion years old, would fall in early March. The oldest fossils would show up in late March. Animals have been having hard shells, arrived about 400, oh my gosh, sorry, getting tongue-tied now that I've been talking a while. 542 million years ago, about the middle of November. So that's what I was talking about. The Cambrian explosion occurs on this scale on about November 18th. Okay, the middle of November. Then the Mesozoic era starts in mid-December. The Cenozoic era begins around December 26th. Okay, so this is the era that we're living in. It's just this final week of the year. This is the human time scale. Okay, we are just the last week. We are icing on the cake. All right. Here's just another way to view this. We've got the 4 main divisions: the Precambrian, the Paleozoic, the Mesozoic, and the Cenozoic. Those are the only 4 I want you to really focus on remembering for this class. The others are important, but we won't really be using them. So as long as you understand, the Precambrian is the oldest, followed by the Paleozoic, followed by the Mesozoic, followed by the Cenozoic, then you'll be all good for this class. The age periods define on a basis of their fossils and the numeric age calculations. Age periods named from the place where they were first recognized. So if we're looking at the Mississippian and the Pennsylvanian, those are the easiest to see because we're familiar with Mississippi and Pennsylvania. But all of these are related to the locations where the rocks were first found. And the time scale is not set in stone. There was a recent change in subdivisions of the Cenozoic, so these are flexible, and it all depends on what new evidence we can find in the rocks for other big changes that are worthy of a new distinction. Now, what are some strategies for approaching geologic problems? Depending on what the problem is, you're going to look at it in a different way. So how does the question affect the data needed? That's what we're looking at here. We've got the same area, and asking different questions, we're looking at different things. So if the question is, where do we find petroleum, so the image all the way on the left, then what we're looking for is just sedimentary rocks. We just want to know what type of sedimentary rocks here, and is it possible that oil could have developed here? Is it possible it could be trapped here? So if your question is, where's the petroleum, you're only interested in sedimentary rocks. If you change the question and you're looking at groundwater, then you're going to group the rocks based on how well water flows through them. So it doesn't matter if they're the same type of rock or the same ages. It just matters how does water flow through them. So those are the only rocks you're going to be looking at, is the ones that have good flow, because that's where you would want to pump the groundwater out. Then the last question, again looking at the exact same area, if we change the question to where are the earthquake hazards, then we're just looking at this fault, which is this green plane extending down into that right image, and the proximity to the fault. Okay, so what is the movement along it? What are the rock types around it? That kind of thing. So depending on the question, you have to look for different data. Okay, what are the rock types? How does water flow through it? What is the seismic activity? Different data for different questions. The next one is the problem of incomplete data. So looking at this image, we've got this layer of blue in between tan sediments. So this is showing us groundwater. Above that blue line, this is an unsaturated area. There's no groundwater in the land there. So this is showing us the water table. And these little gray things above ground are showing us the wells. So what happens when the data is incomplete? If we imagine drilling water wells in this area, if you can only see what's on the surface, you're going to get a very incomplete view. So we don't always have the data we need. So if we just drilled on the well on the right, and that was the only well in this whole area, we would drill down into the solid rock. We wouldn't be able to draw up any water, and we would say, oh, this place is useless. Nobody can live here. Okay, if we went to just the well on the left and only drilled that one, we would say, oh wow, this water is limitless and everyone can live here. It's only when we put in a bunch of different wells in between each of those that we get a more accurate view of what's really going on. The more data points you have, the better, the more realistic, the more accurate the picture is that you create. Okay, so what happens when the data is incomplete? You get an inaccurate view of what's really going on. You get an inaccurate view of what's really going on. And it's always the more the merrier as far as data goes. The next slide